All right, so I have talked about these graph neural networks before in my playlist for natural language processing. For example, I talked about graph sage algorithm, and there are lots of algorithms for graph neural networks, but today I created a new playlist to explain graph neural networks from just the beginning level. So I start by an application for node classification on CORA. And so you know that graph neural network is more general than just uh, these restricted class of graphs. Let's say they are called grids in graph theory, and they are very restricted. But natural data are represented by graph as it is implemented in our brains. For example, this could be social networks or any other things, or any concept inside your brain. So there are lots of graph neural network libraries, but the one that I use today is spectral. Of course, I like PyTorch, geometric, and spectral more than deep graph library, other graph libraries. And the version that I'm using today, and I will put it on my GitHub, Deep Learning Engineer, is this one, 0.62. And the CORA is a good benchmark for because it has the CORA has 2,708 scientific publications and only 7 labels. So we have 7 topics. So let's come back to this. So SSP, this article is state of the art on this benchmark. I mean, applying graph neural networks on this benchmark, which is a very nice article. And so CORA is the dataset that we are working on. We want to classify topics based on graph neural networks. And we have this amount of nodes in our graphs. And also we have about 5,000 edges. And this is the graph of CORA. And if you run my Google Colab codes, you will see that the number of nodes is 2,708, and the number of nodes is this, and the number of topics is just 7. We have only 7 labels. And we apply softmax cross entropy as a loss, because for any graph neural networks, you need a loss in order to train those weights of the graph neural network. So I just use, the reason that I use mask for all of these, because I divide it into training data, validation data, and test data. And there are 2 great books. This one is just 128 pages, very nice, good summary. This one focuses on about different problems that occurs in graph neural networks. And so, there are many methods. One of them is graph attention networks that I will explain in the next lecture, that we use it for example, we use a variation of graph attention network in order to reduce the dimensionality, because in visualization, for example, if you use TSNE, we are doing dimension reduction. So we can use it with GAN as well. So graph attention network, or GAT. And the graph convolution network is also very popular among these graph neural networks. But because this topic, because I want to show you some codes, so I started from a very elementary vanilla graph neural network. So there are lots of methods, as you know, graph LSTM, and here there are even spectral methods, non-spectral methods. there are many different ways to categorize these methods. And so the vanilla graph neural network, as you see, uses, traditionally goes back to 2005, using the first very elementary type of GNN started in 2005, and then with the same author, this Franco, in 2009. And so the idea is that we want to just learn a state embedding using some weights of the neural networks. And of course, after you created your graph using k-nearest neighbor or whatever algorithm in k-nearest neighbor you use, or even like in the Pinterest company, you use, when the users put some pins, when the duration between their entering is less than 10 seconds, they say that two edges or two images are very similar to each other, so that they can connect it with an edge. So for vanilla graph neural networks, we have input features X. We have, when I say co, it means that features of the corresponding, for example, we have a V, we have node V, and it has some edges. And we use this for the CO. And NE means neighbors. This is neighbors. So we have features and the embedding. Embedding is H and features are X. X is, for example, your input feature. For example, if you have an image, it has, for example, 1024 pixels, and this is the dimension. And you have the output embedding, and you can see it's just a recursive iteration that you can use Banach fixed point theorem to show that it is unique. After a while, it converges, and O here is the output, so it converges to a solution. And but how do we learn this? We need a loss, because otherwise we don't know how to train this and how to backpropagate this, because we don't know any paradigm except backpropagation, for example. For example, if we use this simple loss, you can use just P node, P data points, because you may have, for example, 1 million nodes, but only we have 100 training supervising nodes that have labels. And so you take advantage of them and you train it. But you could also use cross-entropy loss for classification. So because you have some logits, you transfer it, you normalize it, and use softmax to normalize it, and becomes like probability distribution. And then you have cross-entropy, your cross-entropy loss. And we have used cross-entropy loss in this implementation. And as you see, here we use mask softmax cross-entropy for your logits and their labels. But I said that we use a mask, and here we use training mask, just training data. And so we apply, for example, for layer 1, if you want to, for example, units could be 32 instead of lots of, for example, 1000 dimension, you can reduce the dimensionality to 32. And 7 here is just because you have 7 topics, the labels, the number of labels in this graph. And you observe all of the training loss and value loss and test accuracy. And what is important here is just the logits. Use GNN FN, and your GNN is just you transform, and then I will explain what it means. So if we come back, so here we are implementing this. We are saying how these nodes how we are using the neighbors, how we are using the embedding of the neighbors to just update this edge. And this is just an iterative procedure until convergence. So we have implemented this in Google Colab, and there are, of course, some limitations of this vanilla graph neural network. First, it is computationally inefficient to update the hidden states of the nodes. And also, vanilla GNN uses the same parameters in the iteration, while most popular neural networks use different parameters in different layers. I will, for example, in the next lecture, I will explain graph attention, GAT, and then you will see that it matters that which, for example, if you have a graph, you should know this edge has attention to this edge more than another node. So it attends to this node more than the other node. And you can measure these and create attention, and so it becomes a little bit more complex. And these are the results. So if you train the CORA with your features and adjacency matrix and the GNN function, and if you reduce your dimensionality to 32 features only, then after 200 epochs, just a learning rate of 0.01, you can have this nice accuracy. And the electron is a theory, but the theory is so good we can almost consider them real. This is a quote by Richard Feynman. You can think about graph neural networks the same thing, although it is still at its at its infancy, at its basic theoretical development, but you can still use it for practical purposes. Practical problems.